Hi, welcome everyone. I am Dr. Rajkumar from School of Physics and Material Science, Thapar Institute of Engineering and Technology, Patiala. So in this video, we'll talk about RK methods of solving differential equations. So we'll cover the topics RK method up to fourth order. So we'll discuss one by one first, second, third, and fourth RK methods, then corresponding numericals. So in modified Euler method, the slope of solution curve has been approximated with the slopes of the curve at endpoints of each subinterval in the computing the solution. So in previous video we have discussed about the modified Euler method, in which we have considered the slope at the 2 points, whereas in Euler method we have slope at 1 point. So modified Euler method is a better one as compared to the simple Euler method, and faster as well. The natural generalization of this concept is computing the slope by taking a weighted average of slopes taken at more number of points in each subinterval. So we started with 1 point in Euler method, then number of points increased to 2 in modified Euler method. We can also take 3 points in a subinterval, then 4, and so on. So this is a kind of generalization of modified Euler method. The formula for Euler method is yn is equal to yn minus 1 plus h times f of xn minus 1 comma yn minus 1. So what this formula does is, this formula advances the solution from known xn minus 1 value, say x, if n is 1, then from x0 to x1. So given value of xn to next value of xn. Okay, so where xn is equal to xn minus 1 plus h. So it advances the solution through an interval h, but uses derivative information only at beginning of that interval. That is, the step error is only 1 power of h in Euler method. There are various reasons that Euler method is not implemented or recommended for practical use. Among them, first one is the method is not very accurate when compared to other methods which run at the equivalent step size, and neither is it very stable. So it is not always possible that it might converge. The Taylor series method of solving differential equation numerically is restricted by the labor involved in finding the higher order derivatives. So we can use Taylor series method for solving the differential equation, but as clearly mentioned that it involves higher order derivatives, so it is a laborious task. There exists a class of methods known as Runge-Kutta methods, which do not require the calculation of higher order derivatives and produce better accuracy as well. So we have discussed about this Euler method, modified Euler method, then Taylor series of solving differential equation, and a better one, RK methods, which involve only first order derivative, not higher order derivative for solving differential equations. The RK formulae possess advantage of requiring only the function value at some selected points within the subinterval. These methods agree with Taylor series solution up to the term in h raised to power r. And what is r? H is step size, r is called order of that method. For example, RK1, then r is equal to 1, for RK2, r is equal to 2, and so on. For RK4, r is equal to 4. Now, there are 4 order of RK methods, as I have already explained. Let us move on to first method. So let us rewrite the Euler equation. Y1 is equal to y0 plus h times dy by dx, which is equal to f of x0 comma y0. So this is the given function, or y0 plus h y0 prime. So the function is equal to dy by dx and is equal to y0 prime. okay, at x0 and y0. Now expand right hand side of equation y1 is equal to y at x0 plus h by Taylor series. Okay, so this is the value of y1, which is y which depend on x coordinate. So x coordinate corresponding to y1 is x1, which is x0 plus h. So expand this right hand side term using Taylor series method. So y1 is equal to y is x0 plus h is equal to y0 plus h times y0 prime plus h square by 2 factorial y0 double prime plus so on. So this is simple Taylor series expansion. From above two equations, this one and this one, it follows that Euler method agree with the Taylor series solution up to the term in h, since it is first order. So if we consider h raised to power r is equal to 1 for RK1 method, first order method. So the terms of Euler method and in Taylor series method, they matches up to h raised to power 1. Okay. So the Euler method is RK method of first order. So then let us move on to the second order RK method. In this method, the value of both x and y at that midpoint are used to compute the real step across the whole interval. So the modified Euler method is the second order RK method. Okay. The modified Euler formula is y1 is equal to y0 plus h by 2, and we have average plus h is this 1 by 2 is from the bracket, coming out from the bracket. So inside the bracket we have two slopes at point x0 y0 and at point x1 y1. So two slopes. This y1, since we don't have initial approximation of y1, so we used to calculate this y1 from Euler method or import the value of y1 from Euler method. Substitute y1 is equal to y0 plus h times f of x0 comma y0 from Euler method, as I've already explained it. Now y1 value becomes y0 plus h by 2 function x0 y0 as it is plus f of x0 plus h comma value of y1 from Euler method is y0 plus h times. If I write value of f at x0 as f of 0, so notation is changed here. So simply this equation is this one. Now expand right hand side of above equation we get. So if I expand this term, so y1 becomes y0 plus h by 2 f of 0 this term plus in curly bracket f of x0 y0 plus h times curly f by curly x 0 plus curly 0 means at x0 plus h f0 curly f by curly y at 0. Okay, plus other higher order terms of h square. Okay, so this one is I think simple. Simply we apply the Taylor series method. Now on rearranging the terms, we don't get into the details of the terms, how we rearrange it. Simply we reduce y1 to y0 plus h f0 plus h square by 2 f0 prime plus other higher order terms of h cube. I have kept a star in previous equation because the order of h square was there. But here we have considered other higher order terms of h cube. Now expand right hand side of equation y1 is equal to y x0 plus h by Taylor series. So same Taylor series method, y1 becomes y0 plus h y0 prime plus h square by 2 factorial y0 double prime plus h cube by 3 factorial y triple prime. So how much terms these two equations they match? First, second and third. f0 is dy by dx at x is equal to x naught. So this is y0 prime, and this one first order derivative of f0 is y double prime at x0. So up to h square these terms matches. From the above two equations, it follows that modified Euler method agrees with the Taylor series solution up to the term h square. So this Euler method is RK method of second order. So the second order RK formula is y1 is equal to y0 plus half k1 plus k2, where k1 is fx0 y0 and k2 is fx0 plus h comma y0 plus k1. So we have used this value here. So this is a rearrangement of modified Euler method. Similarly, it can be proved that Runge's method agree with the Taylor series solution up to term in h cube for third order RK3 method, but that is not very famous. So RK2, after RK2 we move on to RK4 method, fourth order. This most widely known member of RK family is generally referred to as RK4, the classical Runge-Kutta method, or simply the Runge-Kutta method. So in this method, in each step, the derivative is evaluated 4 times, first order derivative, okay? So 4 different slopes at 4 different points in the subinterval. So at 4 points, 1 at the initial point, 2 twice at the trial midpoint, so in between the subinterval, and 1 at the trial endpoint. From these derivatives, the final function value is calculated. So we don't go in the details of how we calculate. We simply move on to the functions we get following the same procedure as in the previous one. So the simple formula for RK4 method is yn plus 1 is equal to yn plus k1 by 6 plus k2 by 3 plus k3 by 3 plus k4 by 6 plus other higher order term of h raised to the power 5, where k1 is h f of xn yn, k2 is h f of xn plus h by 2. Okay, so this is midpoint of the interval, comma yn plus k1 by 2. So we are using this k1 here. So k1 is the value of ordinate or y at midpoint. Then k3 is equal to h f of xn plus h by 2 as it is, comma yn plus k2 by 2. So k2 is this one. So in this we are reiterating the terms for getting better accuracy. Then k4 h f of xn plus h, this is the trial endpoint of the interval, comma yn plus k3. So this one. So these two terms, they corresponding to the midpoint. This one is the first point of the interval, and this one is the corresponding to the last point of the interval. So this is the formula for RK4 method. Okay. So now let us move on to the working rule of finding the increment k of y. So y1 is equal to y plus k. So we have to find the increment in y, that is k, corresponding to increment of h in x. So x1 is x plus x0 plus h. By RK4 method, for equation dy by dx is equal to fxy, where given that y value is y0 at x is equal to x0, is as follows. So calculate successively value of k1, k2, k3 and k4, and finally k comes out to be 1 by 6 of k1 plus 2k2 plus 2k3 plus 2 simply k4, or you can also include this factor of 1 by 6 here as well, no issue. So this gives, so if we add this value of k in y0, we get y1. So y1 is equal to y0 plus k. So this is our solution of differential equation at corresponding to point x1, which is x0 plus h. Now we note that k is the weighted mean of k1, k2, k3 and k4. Okay, so we have calculated the tangent at the 4 different points, and we have taken the mean, weighted mean. Weighted means they have different factors multiplied with them. The operation of this method is same for linear or non-linear differential equation. So this method is same for linear and non-linear differential equations, RK4 method. Now let us move on to solve the numerical. So in this we have to apply RK4 method to find the approximate value of y when x is equal to 0.2 simply. given that dy by dx is equal to x plus y and y is equal to 1 when x is equal to 0. This is simple. So solution is given here. X0 is 0 and y0 is 1. Step size, if we consider as h is equal to 0.2 directly. So value of x at 0 is given, and the value of x at 0.2, value of y at x for x is equal to 0.2 we have to calculate. So we make a simple jump if we consider h is equal to 0.2 from this. So h becomes 0.2. So in one step we will calculate the solution. Then f of x0 y0, which is y0, is 1. Okay, so this is same. So calculate value of k1, which comes out to 0.2, k2 comes out to 0.24, k3 which comes out to 0.244. You see, only the decimal places they are improving. The first decimal place remains the same. K4 is 0.2888. So finally the value of k comes out to be 1 by 6 of weighted average of these k1, k2, k3 and k4, which comes out to be 0.2428. So simply if we substitute the value of k in this equation, which is y1 is equal to y0 plus k. K is the increment in y0 when x takes increment from x0 to x0 plus h. So simply y0 given 1 plus k is computed from this step 0.2428. So finally corresponding to x is equal to 0.2, we have y, which is y1 is equal to 1.2428. So this is how we applied simply the classical RK4 method for solving this equation, and we get the solution in few steps. Okay, so in this video we discussed about the various RK methods, first order, second order, third order and fourth order, and we have seen that RK1 method is Euler method, RK2 method is modified Euler method, and in general in all the orders basically we are increasing the points at which we are taking the tangent. So for first order we are taking the tangent at 1 point only, for second order at 2 point, and similarly for the fourth order we have taken the average slope at 4 different points, at 2 extreme points and at 2 middle points as well. So this is all about the simple RK method. Thank you for watching this video.